Hello, my name is Professor Jong-won Kim, working at Department of Mechanical Engineering of Seoul National University. Today I'm going to talk about geometric tolerance. At last lecture, I discussed the dimensional tolerance. At the time, do you remember the procedure of selecting proper dimensional tolerance? What was the first step? The first step is to select the level of accuracy, class of accuracy, right? Which is represented by IT class. IT is the international tolerance, IT class, right? So the number of IT class is higher and higher, then the accuracy is very poor, okay? If the number of IT class is lower and lower, the accuracy becomes very, very tight, right? And what was the second step? Second step, now from the IT class, you can select the narrow meaning of dimensional tolerance, the range, right? Allowable range. Allowable range is tight and tight, then the accuracy is very higher and higher, right? So step one, you select the allowable range. Then, in second step, you have to select the upper limit and lower limit, right? And the difference between upper limit and lower limit is the allowable range, okay? Right. So in step one, if you select a certain allowable range from the IT class, but there are so many combinations of upper limit and lower limit, right? So, and usually the dimensional tolerance for shaft is smaller than, usually smaller than the nominal dimension, right? And the hole which is shaft is inserted, the size of hole is usually larger than the nominal dimension, right? Anyway, the upper limit and lower limit, if you try to select the upper limit and lower limit at the step two, then first step is, firstly, you have to select the fitting system, right? I told you that there are 5 fit systems. So first one is a loose fit and cross fit and precise fit and press fit and shrink fit, 5 fit. So you have to select the what fit system is proper for considering the function of the part, okay? Right? And then, according to the fit system you select, then there are tables which shows the combination, right? Combination of hole and combination of dimensional tolerance of hole and shaft, okay? Then, based on that table, you can select finally you can assign dimensional tolerance, right? So by that way, you select the dimensional tolerance, right? Okay, but interchangeability is the key to mass production, but only dimensional tolerance you can achieve it. You cannot achieve it. So finally, you have to select the geometric tolerance. So geometric tolerance is the key subject of today's lecture. So both dimensional tolerance and geometric tolerance, you can secure the interchangeability for parts, and then mass production is possible. So I like to emphasize again that the contribution of Mr. Ford, who is the real engineer, to mass production is that he set up the system of tolerance, right? only the conveyor system that cannot realize the mass production. Okay, and my question is that could you secure the interchangeability with my drawing distributed to you for homework? This is the drawing for homework 14, and this homework you at this homework you really manufacture the parts which obey the dimensional tolerance of this drawing. Then I try to select the randomly of the pinhole and hole plate, pin plate and hole plate. Then try to combine it, assemble it, but clearly from my drawing the interchangeable, or it could not guarantee the assembly of the pinhole and hole plate, pin plate and hole plate, right? So at the time, what was the checkpoint? At the time, you have to consider the worst case. Worst case is what? When you select it is a random selection though. You select the MMC hole plate and MMC pin plate. What is MMC pin plate? MMC pin plate material maximum condition. So pin plate, the size of pin is largest, right? And hole plate, MMC hole plate. What is MMC hole plate? Then material maximum condition is when the hole is smallest, right? Then smallest hole and largest pin, try to insert it. Then the center distance of MMC pin plate and MMC hole plate is the problem. Why? The center distance, that is at center distance 70, the general tolerance was assigned based on my drawing. So general tolerance, which is given to the center distances, are the problem for the interchangeability. So my drawing is not proper for the interchangeability. So at the final slide of this lecture, you can see the solution. Okay, so please, and that solution includes some geometric tolerance. Okay, so that is why this lecture is very important. Okay, dimensional tolerance and geometric tolerance. The geometric tolerance is no manufacturer can massively produce parts which have the perfect true dimension, right? So in this case, the true dimension is the out is 100 millimeter. So no mass production of true dimension is impossible actually. So anyway, you have allow some you have to assign some allowable range, which means dimensional tolerance. And also in geometric tolerance, no manufacturer can massively produce parts which have the perfect true shape. In this case, true shape is true circle, right? True circle. So in same sense, in dimensional tolerance, in geometric tolerance, you have to assign some allowable range of what? Allowable range of shape variation. From the allowable range, which can vary which can be vary from the true circle. Okay, all right. So that is the concept of geometric tolerance. So, but before I explain you the details of geometric tolerance, you have to understand that dimensional tolerance and geometric tolerance are independent with each other, which means that if you see the dimensional tolerance of 30 plus minus 0.04, then some people may discuss that since this from the allowable range, maybe for example, if this edge, the length is 30.04 and this length is 29.96, then you may assign there, since there is a range of 0.08, so maybe someone maybe discuss that from the based on the lower plane, the upper plane maybe the parallelism, maybe the range of parallelism maybe 0.08, right? But yeah, so there are so much discussions on this, but finally the ISO claimed that dimensional tolerance does not restrict the geometric tolerance. Okay, so both are independent with each other. Because for example, for window glass, you know, thickness given by the thickness of window glass thickness may be given by general tolerance. Yeah, the thickness is not problem for considering the function of window glass. The thickness may be vary, but it's not important. But the parallelism of the top to bottom plane is very important, right? Window glass. Considering the function of window glass, the parallelism is very important. Thickness, if it is parallel, then the thickness may be vary according to the general tolerance. It's no problem. But the parallelism is the key function of the window glass. So the parallelism have to be assigned a little tightly, right? Thus, dimensional tolerance and geometric tolerance are independently assigned. It's very reasonable, you know. So in this drawing, 30 plus minus 0.1, that is a general tolerance, the thickness. But the parallelism, this is a symbol which means parallelism, which I will talk about in details in later slide. So don't worry about it. The parallelism symbol. So according to this is the based on the top plane, the parallelism of the bottom plane, the parallelism of the top plane is assigned. The parallelism is assigned 0.02 millimeter, right? So, okay. So since there are so many cases like this, considering the function of the part, so dimensional tolerance and geometric tolerance are independent. Okay. Do not try to mix up with the dimensional tolerance and try to get some meaning from the. Never try to get some meaning from the dimensional tolerance. Never try that. Both are independent. Okay. All right. Now, since I this is what I what I did talk about in last lecture maybe. This is the connector, part of connector. Then at the time, what did I told you? That try to assemble the pipe on the plane vertically, right? Vertically, okay? Then at the time, so I I told you that assembly skill is not important. Okay? In this case, the vertical posture to the plane is determined by the accuracy of this part, the connector, right? And the accuracy, especially that accuracy, should be assigned by the geometric tolerance, perpendicularity of the axis of this cylinder. This cylinder should be assigned based on the bottom plane of the connector, right? So that perpendicularity, which is one of the geometric tolerance, is determining the vertical posture of the pipe to the plane, right? Okay, so this is the example of the importance of geometric tolerance. And this is another case precisely spinning spindle. So this is a spindle, is spinning, and the bearing is inserted. So, and then this is the bearing housing, and this is a main body. So, and the runout magnitude is very important. The runout, which is one of the geometric tolerance, so which I'm going to explain in a later slide. And anyway, if you disassemble this unit, then you can see there are so many parts. So this is a bearing housing where this bearing is inserted and sustained. And now, and spindle runout is the spindle runout, which is the geometric tolerance. And if the perpendicularities of the inner and outer side planes to the bearing housing axis are not good, then which means that this is the outer side plane and this is the inner side plane, and the perpendicularity of these two planes to the cylinder axis is not, if I exaggeration, if it is the perpendicularity is like this, then what problem is that if you assemble the spindle into the bearing housing, and then since the bearing the posture is distorted, then and then it is natural that the spindle runout becomes large. Okay, so the runout magnitude, which is one of geometric tolerance, is determined by another geometric tolerance of perpendicularity of the planes to the cylinder axis. Okay, so this is another example which shows the importance of geometric tolerance. Okay. Okay. So if you want to reduce the spindle runout, then you have to assign geometric tolerance as follows to the bearing housing. So this is all symbols for geometric tolerance. So I'm going to explain it one by one by next slide. So datum, there are, the one terminology is datum A. Datum A is the axis A. So now datum A indicates the features of the axis of this cylinder. Okay, why? Because A, this is a whole A is now the line is attached to the dimension line of pi 100. Now you see H6 is the dimensional tolerance. So since it is attached to the dimension 100, so it's 100. So A is now the axis of 100 axis, right? So, okay, and so A is here. A means the axis, since it is attached to the pi 100. So, okay, axis. Please remember, A indicates not the cylinder itself. What? Axis of the cylinder. Okay, A. Okay. Now, the roundness. Now, it means you can see the small circle. The symbol of this symbol means the roundness of the cylinder surface, which owns the datum A is 2 micron. It's very, very tight roundness. Very, very tight roundness. Maybe you have to use very precise grinder, okay, or you need a very precise jig boring machine tool. Which we call it jig boring. Anyway, okay. And the cylindricity of the cylinder, this symbol using two small parallel line on the small circle. This symbol is the cylindricity of the cylinder surface, which owns the datum A, is 3 micron. 3 micron, very tight cylindricity. Okay, roundness is related to true shape. So the definition of roundness is here. The circular shape of the part, okay, circular shape of the part must lie between two concentric circles, whose sizes are different with each other by t in radius. So by t, right? This is a two concentric circles, okay, and t in radius, okay. If within this area, between two concentric circles, if this circular shape is lie inside it, then the roundness, the geometric torus roundness of 0.02 is satisfied. Okay, right? Okay. So, but two concentric circles are chosen, which means that there are so many concentric circles which can enclose this circular shape. There are so many combinations, right? If you change the center of the two concentric circles, then you can generate two concentric circles which enclose this true shape. There are so many combinations. So two concentric circles are chosen in such a way that the size t in radius should be minimized. Right? So to find out the roundness of the circular shape is some trial error. Okay? So two concentric circles, you have to try to make two concentric circles with the center is same, and two concentric circles which can include true shape in inner part and outer part, outer side and inner side. Okay, then you have to find out two concentric circles whose t is minimum. Okay, t is minimum. Then you can tell the roundness of this circular shape, right? Okay, so by that way, the roundness is determined. So now the the circular shape, the roundness assigned, this is a symbol of roundness, so symbol roundness assigned 0.03, then this circular shape should be lie inside the two concentric circles, right? Okay, with whose t is 0.03. Okay, so right, this we call it tolerance zone. So tolerance zone is a geometric zone within which a line, surface, a cylinder axis or a whole axis of the part must lie for the part to satisfy proper functioning and interchangeability. Okay, so in roundness, the tolerance zone for roundness is in yellow area. Okay, yellow area, whose t is 0.03. Typical number is designated to represent the size of the tolerance zone. Okay, all right. Okay, all right. So so the typical number always defined by millimeter, designated by millimeter, unit millimeter, right? So in geometric tolerance, even if it deals with the shape, the dimension shape, but the typical number which represents the tolerance zone is millimeter, distance unit. Okay, if it is a perpendicularity, it is not designated by angle, degree. Even if it is a perpendicularity, the typical number is designated by millimeter. I will explain it in later slide. Okay. All right. Cylindricity, roundness is extended to the axial direction. Roundness is a true circle. It is extended to the axis direction. Then it is a cylindricity. So this is the extension of the roundness. So the surface of the cylinder must lie between two concentric cylinder surfaces. In this case, cylinder surfaces. In roundness, concentric circle. But in this case, it is a concentric cylinder surfaces, whose sizes are different with each other by t in radius. By t in radius. Okay. Right? Okay. So this is the symbol, cylindricity symbol is here. So cylindricity 0.1 means that the surface of this cylinder is here. This is a true cylinder surface. Must lie between two concentric cylinder surfaces whose sizes are different by each other by t in radius. So in this case, t is 0.1. So this is the tolerance zone. Okay, all right. There are another geometric tolerances assigned to the bearing housing, which is the perpendicularity of the plane. Okay, which is the perpendicularity symbol. This indicates to the datum A are 0.003 and 0.01 millimeter respectively. So this is a symbol of perpendicularity. So perpendicularity is the relative properties. So it should be from datum A. From datum A, the other plane, a plane is defined. The perpendicularity of the other plane is defined. So, the plane which designate this symbol is this plane. So let's follow this line. Then you see this small plane here, the small plane. The perpendicularity of this plane to the datum A. Datum A is the axis of the cylinder, whose diameter is 100. So this perpendicularity is 0.003, 3 microns, very tight geometric perpendicularity. And another this is another perpendicularity. So this indicates the plane of this. So this pink plane, right? The perpendicularity of this pink plane to the axis A is 0.01 millimeter. Okay. Yeah, perpendicularity. It is assigned by the distance unit, millimeter. Okay, another one is here, here. The surface is here, this one. The surface which is hidden from this direction. Oh, sorry. Okay, so, right. That's it. 3 perpendicularities. Right. The meaning of perpendicularity is here. Perpendicularity of a plane. The plane must lie between two planes, which are perpendicular to the datum axis with the distance t. So two plane is here. Two plane, which is parallel with each other, and which is vertical. Both planes are vertical to the datum axis, and the designated surface should be lie within these two planes. So the area, the space between two planes is a tolerance zone whose distance t is 0.08. Okay, then the perpendicularity of this plane from to the axis, to the datum A, the axis is defined. So yeah, A is attached to the pi 30. So A means the axis of the pi 30 cylinder. All right. Okay. Don't misunderstand that. Never misunderstand that A designated the cylinder surface. Never. It is the axis of the cylinder. Okay. Axis of the cylinder. Right. Okay. Now, perpendicularity of an axis. The axis must lie within the cylinder here, with its diameter t, which is perpendicular to the datum plane. So now this is the datum A. Datum A is the bottom plane, and the perpendicularity symbol attached to the pi 10. So this means the axis of pi 10 cylinder. So the perpendicularity of the axis of the pi 10 cylinder, according to the A, is pi 0.01. Why pi? Since the tolerance zone here is the cylinder, so whose diameter is pi t. So pi is attached here. So within that cylinder, whose diameter is 0.01, the axis of the pi 10 is contained. Then the perpendicularity of the axis of perpendicularity of pi 10 cylinder, axis of pi 10 cylinder is satisfied. All right. Okay. And the last geometric tolerances assigned to the bearing housing is the concentricity of the axis well, which is the symbol is here, indicates to the datum A is 0.003. So here, okay. So this is the roundness and cylindericity, and this is the concentricity, okay. Concentricity to A. A is 3 micron. A is what? A is the axis. Okay, axis of the pi 100 cylinder axis, and this also, this symbol, concentricity symbol, indicates what? Pi 140 cylinder. Okay, so this indicates the what? Axis of pi 140 cylinder axis. Which one? This one. This is small portion. This axis is parallel to the what axis? This axis. Okay, so the concentricity, the meaning of concentricity, the indicated axis must lie within the cylinder whose diameter is T, whose axis coincides with the datum axis A. So this is a datum A. So datum A, pi 20, the axis of pi 20 cylinder. So this portion, okay? You understand me? This axis is the datum A, and the concentricity symbol indicates what? Another pi 20 cylinder. So axis of this portion. So this portion, the axis of concentricity of this axis to the axis A, datum A, is defined by that this is a axis of this portion. The axis must lie within the cylinder, within the cylinder whose diameter is 0.08 and whose axis is the axis of A. Okay, so then tolerance zone is a cylinder whose diameter is 0.08. Okay, then concentricity is satisfied. So concentricity is actually the two axes must coincide. As it coincides with each other, then the concentricity is satisfied. But definition of concentricity is like here. Okay, so all tolerance zone, the characteristic dimension is all distance unit, millimeter. Okay, even if the perpendicularity, you see, perpendicularity, it is not defined by angle, degree, right? Angle. It is defined by the what? Millimeter unit, right? Okay. So please make it clear, very clear. All right. Okay. And yeah, I explained to you the four geometric tolerances. Okay. All right. And also there are many geometric tolerances which are important. So I will firstly I will explain straightness. The linear shape of the part must lie between two parallel lines whose distance is t. It is the same concept of roundness. Roundness was defined by using two concentric circles. In straightness is the defined by using two parallel lines, right? So two lines are chosen in such a way that the size t should be minimized. Okay, so this is the true shape of the linear shape, true linear shape, and this linear shape must lie between two parallel lines whose distance is t. There are so many combinations of parallel lines which can include linear shape. but in this case, from the so many combinations, we select the one combination whose t is the smallest. Okay, then we can define the straightness. Okay, and the axis of the pulse must, and in this case, we can assign the straightness of the cylinder axis. The axis of the pulse must lie within the cylinder whose diameter is t. The cylinder is chosen in such a way that the size t should be minimized. So this is the straightness of the pi 50 cylinder. So straightness of the axis of the pi 50 cylinder. So the axis must lie within the cylinder whose diameter is 0.08. Then this is the straightness of the cylinder axis. Flatness is in case the straightness is extended to the plane, then we can define flatness. So the plane must lie between two parallel planes whose distance is t. So this surface, the flatness of this plane should be 0.08. Then this plane, the real plane, should be lie between the two planes whose distance t is 0.08. Okay. Parallelism is also analogous to the perpendicularity. So parallelism, the axis must lie in this case. We just say A is what? A is now the axis of pi 20 cylinder. So from that axis A, the parallelism also it indicates the axis of the upper cylinder whose diameter is pi 20. So the parallelism, if the parallelism pi 0.3 should be defined, then if the axis of the upper axis should lie within the pi t cylinder, whose axis is parallel to the lower cylinder axis. Okay, so t must lie in the the axis must lie in the cylinder with its diameter t and whose axis is parallel to the datum axis. Okay, and the plane, if we call the plane, this means the upper plane and bottom plane. So upper plane parallelism is A, is 0.01. So from the datum A, lower plane, bottom plane, from the bottom plane, the upper plane, the parallelism should be 0.01, means that the upper plane lie between two planes whose distance t is 0.10. Okay? So I mentioned at the previous slide the parallelism of window glass. At that time, the parallelism is defined like this. Okay, all right. And and the learn out is very usually used in the shop floor in industry. So because there are so many spinning objects, motor shaft spinning, engine shaft spinning, and the spindle of the machine tool spinning. There are so many spinning objects, right? Right. There are so many, and when you finish the assembly of a spinning object, the first step is to measure the run out of the shaft. Run out means that when the shaft spins, if the precision matters, then the distance between the spinning axis and the arbitrary fixed point on the surface of the shaft must be regulated, right? It includes the surface. So it is regulated by the geometric tolerance of run out. So run out includes the surface roundness of the shaft. If the roundness of the shaft is low, yeah, it is very the roundness of shaft. If the roundness of shaft is high, which means that it is far from the true cylinder, then if it is a spin, then the run out should be large. If the roundness of the shaft is large, okay, it is far from the true cylinder. So if it is spinning, then the run out becomes large. Also, as well as the shaft spinning accuracy. Maybe the concentricity of two axes, this one and this one, concentricity is higher, then the run out would be large. So run out includes the many effects of the roundness and the concentricity. So many effects are accumulated to define run out. Okay. So anyway, the spinning axis, the accuracy. If you like to measure the accuracy of the spinning shaft, then you must measure run out first. Measuring run out is very easy. If you use indicator, the device whose name is indicator, then you can check the run out very quickly and very easily. So, okay. So it is frequently used in the industry shop floor. Okay, it includes, okay, all right. Now this is the final geometric tolerance, which is true position. So true position assigns the location accuracy of the point or line or plane of a part. Right? Usually, it is related to the location accuracy of the point. Okay, the point. So, for this example, in this example, the point must lie in the circle with its diameter 0.03 millimeter. Okay, so this point lie inside the circle whose diameter is 0.03 millimeter, and its center, the center of the circle whose diameter is 0.03 millimeter, its center is located exactly 60 millimeter away from the line datum A. So this is datum A. So the 60, who is enclosed in the rectangular shape, means that the true position 60.0000, very exact distance of 60 from the datum A. So from the datum A, the distance is 60, and exactly 100 millimeter away from the line datum B. Line datum B, 100 away. Okay, 100 is enclosed in the rectangular shape, so it means true position of 100 millimeter. Okay, so right, so the circle, the center is 60 and 10 from A and B, and whose diameter is 0.03. That is tolerance zone of the true position of this center. Okay, all right. This point. Sorry, this point. All right. So there are many different cases, various cases of true position. So in this case, usually a part has the thickness, right? So it is a 3D shape. So true position of a hole with the thickness is defined like this. So in this is a hole, right? Hole, and the true position of the hole axis. The hole axis is defined by, there are three datum A, B, C, and the true position pi 0.08 is defined, assigned. So, which means that the whole axis, the whole axis must lie in the cylinder, So, in the cylinder, so cylinder here, whose diameter is 0.08. So in this case, pi t is 0.8 millimeter cylinder. So we are trying to define the tolerance zone of the whole axis. Okay, whole axis. The whole axis must lie in the cylinder, with its diameter 0.08 millimeter, and whose axis is vertical to the datum plane A. So this tolerance zone cylinder, small cylinder, whose diameter is 0.08 millimeter. 잠깐 나갔다 왔어, 저거. 이거 끊어. 화면에 이게 들어오니까 나갔다 왔어요. 그 diameter is 0.08 millimeter, and whose axis is vertical to the datum plane A, okay? And also whose axis is exactly 85 millimeter away from the datum B, and 이거 처음부터 다시 하자. 여기서부터. Okay. 요 슬라이드 다시. Alright, so now 여기서부터 다시. Okay. Now actually the whole part has the 3D shape, right? So which means that it has a thickness. So many cases, true position, we define the true position of a hole. Not true, maybe. So true position of a hole with a thickness is defined like here. So you see, this is true position symbol. So the true position of what? The whole axis actually, whole axis. The true position of the whole axis is defined from datum A, B, C. So datum A is the bottom plane A, and B is this side plane, and C is this side plane. So from ABC plane, true position of the whole axis is pi 0.08, which means that then now, if you define the geometric tolerance, then firstly you have to define the tolerance zone, right? Now in this case, tolerance zone is a cylinder, small cylinder, whose diameter is 0.08 millimeter, right? Now that whole axis, so the true whole axis of the hole is here. The true whole axis must lie in the cylinder, with its diameter is 0.08 millimeter, and whose axis is vertical to the datum plane A. So whose axis, what axis? Whose axis means the axis of the tolerance zone cylinder, tolerance zone cylinder, whose axis is vertical to the datum plane A, the bottom plane, and also whose axis is exactly 85 millimeter away from the datum B and 100 millimeter from the datum C. 185 true position, right? Okay. So in this case, so since the whole axis, the tolerance zone cylinder, the small cylinder is the axis should be vertical to the bottom plane A. So by this true position, we define the perpendicularity of the hole according to the plane A is also defined. So true position from the side plane B and C and also the perpendicularity of the hole according to the datum A is defined. Both perpendicularity and true position is defined. Okay, right? And of course, to measure the true position of the hole is very difficult in this case. You have to measure the perpendicularity of the hole and also the true position of the whole axis. So, of course, the measurement is difficult, but definition of true position is very, very clear. Very, very clear definition, actually. All right? And also, in case of B, we can define the three axes of the diameter 15 millimeter and H7 dimensional tolerance holes, 8 holes, must lie in each of the cylinders whose diameter is 0.08 millimeter and whose axis is exactly 3 millimeter away with each other in this case, you know. So 8 slash means that there are 8 holes. The hole's diameter is 15 H7 and the true position is pi 0.08 is defined, right? Okay, so it means that there are the 30 and 30, 30, 30. True position with each other is defined like this. Yeah, this is very, very clear definitions comparing to the dimensional tolerance. I will show it using the blackboard. Okay, now this is 8 holes, and now the center line is drawn. Here. So now, if you just depend on the dimensional tolerance, then maybe you can assign the dimensions like this. So maybe this is 30. So 30, and since you try to define the tolerance of since here 0.08, so plus minus 0.04, maybe. Okay. Then if you try to define the tolerance, 30 plus minus 0.04, 30 plus minus 0.04, 30 plus minus 0.04. Then you may think that by assigning the dimensional tolerance like this, yeah, of course, plus minus 0.04 is only the allowable range is 0.08 millimeter, 0.08 millimeter. So very tight dimensional tolerance. But the difference between the this type of dimensional tolerance and with the true position, the assigning of true position in that slide is that the difference is that if you assign in the accuracy between holes by using this dimensional tolerance, then it means that the center, the whole center is within this area. Within this area. Within this area, whose the rectangular shape, the edge is 0.04, and this edge is also 0.04, 0.08, sorry, 0.08 and 0.08. Okay, so maybe it means that the whole center lies in the squares, whose H is 0.08 millimeters, right? Okay, right. But using true position is very, very clear, you know, very, very clear. So true position, then the tolerance zone is represented by the circles. By circles, whose diameter is pi 0.08. Okay? So this is the center must lie within this circles. If you see in the top surface. Okay? Comparing this and that, this is more reasonable. You know? Very reasonable. Also, if you assign true position within the bottom surface, then also it is assigned perpendicularity of the holes. Okay, so this is very, very clear definition for the true position of the hole centers. Of course, measuring the real true position is difficult. Measurement is difficult, but anyway, the definition is very clear, right? So comparing that and this is very nice assignment. Okay, very clear definition. All right, see, review all 8 axes of 15 H7 holes must lie in each of cylinders with its diameter is 0.08 millimeter, whose axis is exactly 30 millimeter away with each other. Okay. Now, you see. So this is very clear definition. Now, if you understand the concept of true position, now we can go to the previous homework. Yeah, this is the final stage of completing the interchangeability of two pinholes and hole plate, pin plate and hole plate. Now, an example of securing exchangeability by assigning true position. Since it has 2 holes and 2 pins, if you just have one pin and 1 hole, then using dimensional tolerance, using the proper fitting system, you can select the combination from the table. So only using dimensional tolerance you can do it. If it's just a hole and pin, just one pair. But now this part has two pins and two holes. So you have to use dimensional tolerance and also the geometric tolerance, in this case, true position. So example of securing exchangeability by assigning true position is here. So 8 dimensional tolerances are assigned to a hole plate and pin plate, considering its proper function. So hole, as the nominal dimension is 10 millimeter, and the hole, usually the hole is assigned larger than the nominal dimension. So hole is, upper limit is 0.3 millimeter, and lower limit is 0. And pin is usually the smaller than the nominal size of 10 millimeter here. So minus 0.2 and minus 0.5 millimeters. All right. Now, if you assign the hole plate like this, so of course the dimensional tolerance here, and pin plate the dimensional tolerance like here. So yeah, like your homework, the pin is smaller and hole is large, relatively large. Now, you can assemble the hole plate and pin plate randomly. My question. It is the same question on your previous homework. Now, the problem is the 50 50-50 is assigned as a general tolerance, 50. The problem is 50. Why? What is the size of MMC hole? Now, if you try to think about the interchangeability, then the first step is what? In case of MMC plate and MMC condition, material maximum condition. So maybe you can assume that the MMC hole plate is selected and MMC pin plate is selected. In MMC cases, if you can assemble hole plate and MMC hole plate and MMC pin plate, then maybe it can be assembled always. So what is the size of MMC hole plate? MMC hole, so maximum the smallest hole size is what? 10.0 MMC. Now the hole plate, the diameter MMC hole plate, the hole diameter, MMC hole diameter is 10.00, and here MMC pin plate, what is the diameter of MMC pin? Maximum size, so maybe 10 minus 0.2, 10 point minus 2, all right? 10, so 9.8. Now this is MMC pin 9.8, the pink area, MMC pin, and this is the hole, MMC hole. Sorry, the English is missing here. This is 구멍 means hole, and this is the pin. So MMC hole is here, 10.0. Now, if you and this is the other extreme cases. Now the center distance of MMC pin. Center distance of MMC pin. Now this is a pin. Maybe it's a small display, but you see the pin plate here. MMC pin. The distance of MMC pin now, according to the MMC pin, the distance is x. Let's assume that the center distance between MMC pin is x. Then if the center distance of MMC hole is x plus 0.2, then it can be assembled. But if the MMC the center distance of MMC holes are larger than x plus 0.2, then it cannot be assembled, right? Okay. Or in the other extreme case, if the center distance of the MMC pin is still x, then the center distance of MMC hole is x minus 0.2, then it can be assembled. But it is smaller. The center distance is smaller than x minus 0.2, then it cannot be assembled. Now, but what is the general tolerance of 50? Center distance of 50. Yeah, so 50, maybe it's 50 plus minus 0.3, right? So in this case, a general tolerance plus minus 0.3 millimeter is applied to the pin distance xp, and to the pin plate, and hole distance xh of the hole plate with its reference dimension 50, plus minus 0.3 is assigned. So there are some combinations that the difference between the center distance of pin plate and center distance of hole plate is larger than 0.2, then so interchangeability is still not guaranteed. So we have to assign the true position of the two pins and true position of two holes. Okay, how? Here is the solution. So maybe since it can be assembled when the xh is what? The center distance of hole plate, xh, of the hole plate must be between 50 minus 0.2 and 50 plus 0.2 based on the MMC pin plate. Okay? then it can be assembled. So therefore, the previous drawings cannot secure interchangeability because it's more than plus minus 0.3. So according to the figures which I showed you just before, if the following is satisfied, then it can be always assembled. When gamma, large gamma means that the difference between the diameter of MMC hole and MMC pin. So gamma, okay. If gamma, so in here, for example, since the MMC hole is 10.0 and MMC pin is 9.8, so gamma is here 0.2 millimeter. The difference between diameter of MMC hole and diameter of MMC pin is now 0.2 millimeter, right? 0.2. 10.0 minus 9.8 is 0.2. That gamma is here 0.2. The gamma, then the center distance is this MMC. This is XH MMC means that the center distance of MMC hole plate minus center distance of so the difference between center distance of MMC hole plate and XP MMC means the center distance of MMC pin plate. Center distance difference. Center distance. The difference is less than 0.2. 0.2 is large gamma. It is satisfied and it is all assembled. Yeah, looking at this figure, right? Okay, so let the dimensional tolerance of the XHB plus minus delta and that of the X MFC pin be plus minus small delta. Okay, then since the maximum difference between center distance of MMC hole plate and center distance of MMC pin plate is here, right? So it can be always assembled if the following equation is satisfied, right? Okay. Now extend the concept of dimensional tolerance plus minus delta and plus minus large delta to the plane. Now this is equivalent to plus minus. Now this is equivalent to here. So the concept of dimensional tolerance plus minus delta and plus minus large delta is extended to the plane, and it is replaced by the true position small delta and large delta respectively. So securing interchangeability by using true position is that if you select any small delta and large delta which satisfies the relationship here, gamma is here. So there is here, then you can select, you can secure this interchangeability. So for example, the previous pin plate and hole plate, since gamma now diameter of MMC pin, MMC pin here, okay, and the diameter of the MMC hole here. Diameter MMC hole is here, so the difference between is gamma. So if gamma, the true position of the pin plate and true position for hole plate satisfies these relationships. So gamma and delta, you can distribute gamma into small delta and large delta. Then you can secure interchangeability. So the example is for the previous case, since the value of gamma is 0.2 millimeter, if you select small delta and large delta as 0.1, so small delta 0.1 and large delta 0.1, then small delta plus large delta 0.1, then 0.2. So it is less than gamma 0.2 millimeter. So respectively, the interchangeability is secured, right? So dynamic tolerance graph is as follows. So gamma is 0.2 and 9.8 is diameter of MMC pin, and 10.0 is the diameter of MMC hole. So small delta. Now you see the small delta. Now which is the final drawing, which is secures interchangeability, is here. So true position point 1 millimeter is assigned to each of the pin distance of the pin plate and hole distance of the hole plate. So here, hole plate 2, this is the same dimensional tolerance, and then true position of pi 0.1 according to the datum A is assigned here. And also the pin plate true position is 0.1 is assigned. Okay, and now this is the symbol of true position of 50. And the other case is you can select it of the true position small delta and large delta which satisfy these relationships. Then you may select that small delta more large. Small delta, maybe you can select the small delta 0.15 and large delta as 0.05. Of course, the summation of these two is less than 0.2, so it satisfies the relationships here. So then you may select like this. The whole plate, the true position is 0.05, and in whole plate the true position is 0.15. Then also you can secure interchangeability. The reason that the true position of pin plate is larger than the true position of hole plate is that since if this is manufactured by machining only, okay? So the true position can be tight rather than the pin plate. If we include the assembly of the two pins onto the plane, then you can consider the assembly accuracy too. So maybe it's very natural to assign more large true position. Larger true position to the pin plate is more natural. So the true position of the pin plate is large than that of the whole plate. But of course, the summation of two true positions should be less than gamma, large gamma, which is 0.2 millimeter in this case. Okay. All right. Now, the final solution. How can you improve the drawing of the homework 14 to secure interchangeability? Now remember that my drawing was that like this, 30 and 0 plus 1 millimeter. So very loose accuracy, and center distance 70. General tolerance was assigned. So now, what's your strategy? Yeah. Okay. Now, what should be satisfied? First of all, the MMC, the diameter of MMC hole, the difference between the diameter of MMC hole plate, okay, and also between the diameter of the okay. Now the first step is what? Now gamma, large gamma. You have to think about large gamma. Large gamma is what? It's the difference between the diameter of the MMC hole and diameter of MMC pin. Gamma. Maybe that should be larger than 0, right? It should be larger than 0. Then right, like a 0.2 millimeter. Then you can assign the true position of the pin plate and hole plate, right? So it should be a positive number. Now look at here. What's the gamma? the MMC diameter of the hole is 30.0. The diameter of MMC pin is still 30.0. So 30.0 minus 30.0 is gamma 0. Okay? If gamma is 0, there is no way of distribute treat position to hole plate and treat position to pin plate. So gamma should be positive. So this dimensional tolerance is wrong, right? Never. If it is such like this, then you cannot secure any interchangeability. So let's say, in my strategy is that now hole plate, maybe the accuracy should be higher. So maybe I can assign the dimensional tolerance 0 plus 0, lower limit 0, upper limit plus 0.3. And pin plate, the pin is shaft, so it should be smaller than the nominal dimension. So maybe my case is 0.2, minus 0.2, and minus 0.5. So what about the gamma is 0.2 here? Gamma is 0.2. So yeah, the gamma is a difference between 30.0 minus 30 minus 0.2, which is 29.8. So the gamma is 0.2, right? So select more tight dimensional tolerance, and also that gamma is larger than 0. Here it is 0.2 milliliter must be satisfied. True position for the pin plate delta and that of hole plate large delta must satisfy these relationships. So for example, select delta, small delta 0.15 millimeter and large delta 0.5 millimeter. Then your drawing is using true position like here and here. Okay. Then this hole plate and pin plate can secure interchangeability. But comparing your homework you did, then in this drawing, the accuracy of this drawing, so maybe since accuracy is very loose, so you can secure the you can achieve this range of accuracy by using knife. It is enough to use knife. You can achieve this type of accuracy. But this drawing, maybe you cannot achieve this type of accuracy by using knife. Maybe in this case, if you change the dimensional tolerance and geometric tolerance, then in this case, using this drawing, maybe you have to use some accurate machine rather than your hands and knife, right? So manufacturing cost becomes higher, right? But you can secure interchangeability. Okay. All right. This has been the today's lecture. So I hope that you understand the meaning of geometric tolerance and also the final strategy of securing interchangeability of your pin plate and hole plate. All right? Thank you.